Hello everybody, this is the second part of my videos on Proton NMR spectroscopy. The first part, I hope you've seen, it's a long video, was about how we interpret the spectrum, and the second part, this part, is an example we work through how we turn a spectrum into a structure. This is essentially mostly what you have to do in exams. They give you a spectrum, and at the end of it, you have to turn that into a structure. Now, it isn't just a case nowadays of here's a spectrum, what's the structure? Often we get lots of other information alongside that, such as a molecular formula or functional group identification tests or other data from infrared or mass spectra, which also adds to our picture. So it isn't just down to this, but this has a major role to play in the elucidation of a molecular structure. So we're going to take you through how to go about doing an analysis. So it's quite useful if you've got a pen, paper ready, then we will be needing to create a summary table for us to record the information from the spectrum. So this is what we're going to do. So here we go. This is the compound we're going to be working on, and you'll see that when it appears like L. So this is the sort of information we get. This compound C8H16O2 is an ester. Now obviously that's crucial for us to build the correct structure and to make everything seem to fit. Also, as you can see, we have the typical Proton NMR spectrum. And of course, we can see the chemical shift scale at the bottom, remember, measured relative to our TMS reference at 0. We can see there are 4 distinct peaks from our compound. And also, we can see the information alongside the numbers, which of course is the integration values, which tell us the number of H's in each of the 4 environments. So let's create the table and allow us to summarize the information we get from this. First of all, let's create the data table. So as you can see, I've put together a table that summarizes the information, create a summary table with a separate column for each peak. I've labeled the peaks left to right, and I've called them A, B, C, D. And of course, you could call them 1, 2, 3, 4, but be careful, don't to mix up the numbers with the letters, of course. So the final assignment is the important point right at the very end. So we've got the peaks, A, B, C, D, the integration values, the chemical shift value and the type of proton that is, the splitting pattern and what that means, and the final part is the assignment, that is the interpretation, what the data tells us. It's bringing it all together. So once you've created your table like this, then we're going to take you through the stages of the analysis. So the next step is obviously number 2, enter the integration data. So for peak A, the number is 2, B is 2, C is 3, and D is 9. Just a little check here. Check that the total number of protons that you have been given is, of course, equal to the number of protons in the molecular formula. And, of course, this is 16. Please make sure that the numbers are equal. If they're not, it might be a case of multiples. That's relative integration values as opposed to the actual ones. But it still does the same job. So that's the integration numbers. So what that means, of course, is that in peak A, there are 2 hydrogens in that particular environment. In peak B, there are 2, and in peak C, there are 3 hydrogens in that environment. Peak D, there are 9, which of course is different and interesting, but is of course 3 lots of 3. Also interesting that 3 H's can and usually tends to be the end of a molecule in the form of a methyl group, perhaps. Okay, so let's move on to stage 2. Once you've got the table, past the integration, let's look at our data sheet. You're going to need the data sheet, or at least have it handy for the next part. So from the data sheet, use the chemical shift data. Now obviously pick the more or less the middle of the peak if you've got a sort of spread out peak with lots of subsections to it. For example, peak A, as you can see, has got 4 parts or is a quartet. So kind of pick the reading for the shift scale out from the middle of that spectrum. So I've recorded here that peak A is a chemical shift 4.1, peak B at shift 2.2 delta parts per million, peak 3 at 1.3, and peak D at 1.0. Now, of course, the data sheet will tell you what these things will be. Be careful, remember, it is an ester, so you expect to find groups containing carbon and oxygens. So from the data sheet, peak A, I reckon, will be hydrogen bonding to carbon, single bonding to oxygen. And of course, we expect to get things like that on the single oxygen alcohol side of our ester. Peak B, these are hydrogens bonding to carbon that bonds to the carbonyl group, which of course also we'd expect to find in our ester on the carboxylic acid side. Now peak C and peak D both occur in the same band or zone on your data sheet. These two are rather common, of course. These are hydrogens bonding to carbon, bonding to more hydrocarbon. So you'd expect to find these things, of course, on any or most organic compounds. But there are 2 peaks in the same environment, and of course they're not the same thing. Now, the next level of analysis we go to, of course, is to not the splitting just yet, but to actually create the structure that our shift and integration values are telling us. So for peak A, there are 2 hydrogens bonding to the C with a single bond to oxygen. And in peak B, there are also 2 hydrogens on the carbon which bonds to the C double bond O group. There are 3 H's on that peak at 1.3 peak C. Well, of course, that 3 H's is, of course, a methyl group which bonds to another hydrocarbon part. Now, 9 H's in that same type is, of course, 3 methyl groups. So the carbon is joined or has bonding to it 3 CH3 groups. Well, of course, when we put all that together, this is what we find. So I've combined the number from the integration with the actual identification of the proton from the data sheet, and I've drawn in the assignment box what that means. So the CH2 single bonded to an oxygen is of course part of the ester group, the alcohol side. Similarly, the CH2 bonding to the carbonyl C double bond O is of course on the other side of the ester group. And if you look at the ester basic structure at the top, then you can clearly see we must have hydrocarbon parts labeled R and R on either side of our ester link or ester group. We have a methyl group, which of course means the end of a molecule. We also have a carbon with 3 methyl groups on it, which clearly is the other end of the same molecule. So we've got 4 component parts. But of course, which bit goes where? It might be easy with a jigsaw of 4 pieces, but that's not a jigsaw. We have to make sure that the molecule fits and that everything is bonded to the correct part in the correct order, otherwise the structure might be wrong. Here's where the splitting pattern comes in. The splitting pattern is very important. The splitting pattern tells us the identity and number of the adjacent protons. The splitting pattern is of course simply read off by counting the peaks and the sub-peaks of those. So peak A, of course, counting the sub-peaks, is a quartet. Now what that means, of course, is using the n+1 rule in reverse, the number of adjacent protons is the splitting pattern number -1. So what that means is our quartet, or 4 take away 1, means there must be 3 adjacent protons to our CH2O group. So what I've done in red there is I've drawn on the CH3 group, which is adjacent to our group in question. There's 2 H's on a carbon single bond. Well, of course, what that's done is it's created a terminal for our molecule. We know on the alcohol side what the end must be. And of course, that's the OCH2CH3 group. Well, of course, our ester group also, of course, contains peak B, and that is a singlet. Well, of course, 1 take away 1 means there are 0 adjacent H's. That means our CH2 on the C double bond O group has to be bonded to something, but it is bonding to something that does not have its own protons. It has no protons, and therefore there will not be any splitting of our CH2 C double bond O group. Well, of course, peak C, we can already recognize the fact that we have a triplet there, is that means 3 minus 1, that there are 2 adjacent protons. Well, this, of course, is the other part of our alcohol group side on the single bond oxygen. This is confirmation that our methyl group on the end is correct and is immediately bonded to a CH2, which is why we got the triplet. So therefore, peak D must be the other end of the molecule, and of course must be on the CH2C double bond O group. And of course, remember that peak B is not splitting. The peak there is because the atom that the CH2C double bond O is bonding to has no protons of its own. And if you look carefully, of course, the carbon with 3 methyl groups on it has no protons of its own. And so the CH2 must bond to the carbon with the 3 methyls. That must be the other end of the molecule. Well, the final step, of course, is to put all of that together. And so here are our 4 suspected chunks, A, B, C, D. And as you can see, I've assembled them into the only possible correct sequence. We knew from our ester group, we have our OCH2 single bonded oxygen, and of course the terminal CH3 must have been bonding to that. On the carboxylic acid side of our ester, the carbonyl carbon bonding to a CH2, which of course was not split because the carbon on the terminal end with 3 methyl groups has no H's of its own. So when we put all 4 bits together, we create our proper finished ester structure, and of course this is ethyl 3,3-dimethyl butanoate. That's our ester, ethyl 3,3-dimethyl butanoate. The ethyl, of course, is the alcohol side, and the 3,3-dimethyl butanoate was the carboxylic acid group. So we've done a first run through of a confirmation of a molecular structure, and so in the next slide we're going to give you an opportunity to have a go at yourself and try your own analysis on a molecular structure. Okay, so this is spectrum to structure part 2, and I'm giving you a spectrum like this one, and as you can see, I've given the fundamental information of the shift. As you can see, shift scale, we've got peaks labeled A, B, C, D, what going across left to right, and I've put the integration values in red, as you can see, so 1, 1, 3, and 3. And as you can confirm from the molecular formula at the top left, there are indeed 8 H's. There are also 8 H's from the integration values. So create your analytical table, peaks, integration, and shift values, splitting patterns and assignment, and for the 4 peaks. And have a go and see how you can get on with this. Pause the video, because obviously I'm going to show you how to get the answer when you've had a go at it yourself, but not, of course, until. Okay, so here is your question, and I hope you've had a go at it, and let's see how we got on with that. So in the first slide, you're going to see my attempt at the table, and here it is. I've kept the size of the spectrum big as I can so that we can see data and information clearly. And I've made the table, obviously, I've used the initial letters of the headings, peaks, integration, the shift, splitting, and assignment, so that we can obviously fit the table in. But the same idea is to do the analysis as we would have done previously. So number of peaks, of course, is 4. The integration values are 1, 1, 3, and 3 respectively. The chemical shift values we read off from the middle, if you like, of the peak. So peak A is something round about 4.2. Peak B is about 3.6. Peak C we've got here as 2.2, and peak D about 1.3, that kind of thing. So the shift values, obviously, from the data sheet will be revealing us information for the different types of protons. So let me put the information in the table. Hopefully you managed to do this. And the information tells us the shift value 4.2 is a H on a carbon single bonding to oxygen. A peak at 3.7. Well, we've got here an OH group. Now, more about that. Remember, OH groups, we wouldn't normally be able to tell what this is without other information. So this C4H802 has an OH group. There will be a chemical test, or there'll be an explanation or some evidence to enable us to come to that conclusion. Well, of course, we have another well-recognized peak. We have a carbonyl oxygen, single bonded, that is, to a C with 3 H's on it. This is obviously our H on a carbon bonded to C double bond O group. And because it's a 3H on that carbon, that must be the end of the molecule. And also we've got in peak 4, we've got just a single H bonding, as you can see, to a C with an oxygen. And unsurprisingly, we've got here a terminal methyl group, a carbon with 3 H's. And you can probably tell why we have the doublet as well, because there is a single H only bonding to the carbon with the 3 hydrogens. So the methyl group has a C with an H and a single bond O on it. So when we've got the 4 parts to this molecule, then we clearly have to assemble it into a recognizable structure. The information, of course, in the assignment, of course, makes use of the fact of the splitting pattern as well. So if we have a quartet, then we must have an adjacent carbon with 3 H's on it. So our single H on the carbon bonded to an oxygen must have a methyl group on the other side. OH groups, like NH groups, are never split because, of course, the H is bonding to an oxygen, not a carbon. And so the final structure, when we put the whole thing together, is the combination. As you can see, we've got the two end groups, which are in this case both are methyls, and we've also got evidence for a carbonyl group, which is the C double bond O group next to the methyl, so that's one. We also have evidence of a CO single bond, which of course is the carbon with the H on it, and as clearly also has an OH. So the OH group by itself doesn't split, of course, and then we have the other terminal methyl group, which, as you can see from our structure, is the group, as you can see on the end. Clearly, the doublet signal is the peak at 1.3. That doublet signal is caused by the solitary H on the carbon next to the methyl group. Okay, so the two singlet peaks, the little one, peak B, is our OH group peak. That's the hydroxyl group. And of course, the other singlet peak, which is not split, is the three H's peak A, which is bonding to the C double bond O. And of course, there is no other H on that, which will mean that that peak would split. So it's a singlet peak because it's a terminal CH3 C double bond O group. When we put the information together, the only structure that makes any relevant sense, of course, is to come up with 3-hydroxybutanone. The exam board like things in this particular type because, of course, the infrared spectrum would show the carbonyl group in its classic right in the middle of the infrared region, about 1680 to 1820, the C double bond O group, and of course the OH in alcohols group, which shows up as a strong broad peak to the left of the spectrum between about 3200 and 3600 wave numbers. So it is a classic exam question which features a carbonyl and an OH group. This, of course, is deliberately there to try and fool people thinking a CO and a OH means a carboxylic acid. Well, of course, it clearly isn't. Okay, that's the end of our little run through. I'm sure hopefully you've managed to follow what we do with these and that you can have a go at solving some puzzles for yourself. Thank you.